My name is Scott McMillan. There are going to be some talks later on GraphBLAS, and I was asked to give kind of an overview of what that is. So the change in schedule is pretty good. I get to go first before everybody else starts talking about it. I'm going to give you an idea of what this whole GraphBLAS thing is about. Word from our sponsors. Okay, so I am going to talk about the philosophy of GraphBLAS, I think. Okay.
Here in the microphone.
I think we all know graphs can be represented as matrices, in this case adjacency matrices. Basic graph operations can be performed with linear algebra in this case. And these operations can be composed to implement useful algorithms. Okay. And we get our inspiration from something that happened back in the 70s with the BLAS, basic linear algebra subprograms for dense linear algebra. It was an API specification, and its goal was to separate the concerns between low-level library writers who optimize for hardware and high-level application writers who really shouldn't have to know about the hardware that they're running on. So if you can compose an application using calls into the API, you depend on a highly tuned library implementation for your hardware target. You should get some performance portability in this approach. So BLAS 1 came out in 1979. That was vector operations. BLAS 2 in 88, and BLAS 3, which was matrix operations in 90. In the early 2000s, there was a sparse BLAS effort, which could have translated into graphs in some sense, but there was a little uptake. There were things lacking in that approach that in 2013 we decided to do something about. So this effort kicked off, the intent kicked off in 2013. It really got started in 2015 in an effort to define the standard building blocks that would help graph processing. This is a brief timeline. 2013 is the beginning of this. I mean, people have been working with adjacency matrices for graphs at least since the 50s. There was a book in 2011 called Graph Algorithms in the Language of Linear Algebra that a lot of this work was based on. So that really is kind of a good starting point for what we've been doing. The first version of a C API specification came out in 2017. And the first conformant, I'll put that in quotes, we don't enforce conformance, came out later that year. It is a sweet sparse GraphBLAS implementation by Tim Davis at Texas A&M. Those are the blue numbers, so he's been releasing on a regular basis. At the same time, we've been updating the spec on a little bit slower pace, as would be expected. The last release was in 2021, version 2.0, and there are people working on 2.1. I was involved in everything up to 2.0, and since then I've transitioned to specifying C++ APIs because I'm involved in the C++ standardization process, and there's graph libraries that are being proposed over there. So a lot of that is going on right now. I think after C++, we're going to focus on distributed, and Tim Matson is going to be talking about that at the end of the day. So GraphBLAS just consists of a couple of things. We have basic objects. We have matrices that can be sparse or dense. We can have vectors that can be sparse or dense. They are opaque. We don't dictate what the data structure is in the background because we found that different graphs benefit from different types of data structures depending on their density, their degree distribution, and things like that. And we also have algebraic operators. So it's not just arithmetic plus and times. We can support any semi-ring. And I won't get into all that, but you can do min plus semi-rings. It's still linear algebra. You get, shortest path type algorithms from the same operations. So we have matrix, matrix vector. We have element-wise operations, both plus and times. We have extraction of some matrices out of a larger one, and then also the opposite, right? Plus reduction, transpose, a whole bunch of other things. But those are the big ones. Just happened. Glitch. Yeah, okay. So let's get back to graphs as matrices. In case you're not familiar with this, we have a graph on the left. We have its equivalent adjacency matrix on the right. Vertices correspond to row indices and column indices, and edge is an element that is stored in the graph. So the green edge here that goes from 6 to 3 would be element 6, 3 in the matrix. So the sources are the row indices, the destinations are the column indices. If you want to find out which neighbors feed into you, you can look at a column. So any destination node is, you look at the column, you can get its sources. Likewise, if you look at a row of a graph, you can find out who you can reach. And that's probably the more prevalent operation. If I'm somewhere, I want to know where I can get to. So that is essentially a matrix vector multiply. If we transpose the graph, or the adjacency matrix, and we set up a vector that has the source vertices indicated by some stored element. I'm using dots here. I'm not saying they need to be integers. There's lots of different types that GraphBLAS can support. And you do the process of a matrix vector multiply, you get a vector that has a set of elements that are set that are correspond to the destination nodes. So if you want out neighbors, you use A transpose. If you want in neighbors, you use A. Did it switch? All right. I'm going to rearrange it for this talk. This is what the matrix vector multiply looks like. An element in the vector basically picks off columns in A transpose. Those transition to the output. So, and there's one more interesting thing about GraphBLAS besides semi-rings and the fact that we don't dictate data structures, is that every operation supports a right mask. So sometimes we're not interested in certain elements. So if I'm doing traversal and I don't want to revisit things, I mask them out as I encounter them. We provide support for a mask. So in this case, if I'm not interested in visiting node 0 again, I have a mask where node 0 is set, and it blocks the writing of the output for that particular node. We have a mathematical notation, courtesy of Gabor. So this is what a masked matrix vector multiply looks like when you write it out in math. Okay, so what do we want to do? We want to write algorithms in terms of these operations. I'm going to give you an example of breadth first search. In breadth first search, we want to start at a source node, and we want to find out how many iterations it takes to get to all the other nodes that are reachable. So the source node will get a 0. Its immediate out neighbors will get 1s, and then their neighbors, unique ones that we haven't visited before, will get 2, and so on and so forth. So in the first step, we set up the source node. So we set the element of the nodes that we want to start with, in this case node 0, that's in the F or frontier vector. We want to record in our output vector the fact that we encountered it at iteration 0. So we're just basically going to use the structure of F to set something in B. That can be done with a scalar vector multiply with an accumulate. We use the structure of V as the mask, and then we perform the matrix vector multiply. So from 0, we can reach 1 and 3. They pass the mask and write into a new frontier vector, F prime. And then in the next step, we're going to use F prime as the new frontier and repeat the process. So the new frontier is used to set the V vector. The new frontier is used in the mask matrix vector multiply. And we'll see that node 1 can reach 4 and 6. Node 3 can reach nodes 0 and 2, but 0 is going to get masked out because we've already visited it, and then everything propagates to the output. This is the third iteration. the frontier of 2, 4, and 6 can reach 5. We can reach 5 two ways. So in a matrix vector multiply, when we have 2 ways to get something, you actually invoke the plus operator in your semi-ring. In this case, we really don't care how we got there, so either one is valid. This corresponds to the benign race in the graph 500 thing. Either one sets the value. So if I were using booleans, either one sets true. It doesn't really matter. I don't have to do a reduction. And then in the last step, we have to do one more just to make sure that we don't find anything new. When the new frontier is empty, we exit. And so breadth first search can be written in a few math operations. This is about as many operations as the actual GraphBLAS call. So I'm going to get to conclusions. There's a lot of work going on. I've talked about the API and how you would use it. It's pretty low level. It is for people who want to develop algorithms. It's not generally for end users. There is a very good implementation of the GraphBLAS API in C called SweetSparse by Tim Davis. It is an open source repository. You can go out to GitHub and get that. But on top of the GraphBLAS, we've been starting to develop the algorithms. We're trying to reach the users. So we're writing a bunch of algorithms. We did all of the GAP benchmark algorithms a few years ago and participated in a benchmarking activity with Intel and like 4 other graph frameworks. More recently, and Gabor will talk about this, is he's implemented the Graphalytics algorithms that are getting into LAGraph, and that'll be in the LAGraph 1.1 release. But more exciting is the fact that we've got language bindings on top of C and eventually C++, because I heard yesterday nobody wants to use C++, everybody wants to use Python. So the folks at Anaconda have written Python bindings. There's actually 2 sets of Python bindings, but Anaconda is the more active project right now. So they sit on top of the API. They make calls directly into SweetSparse or into LAGraph. And now, more recently, they've integrated themselves into the backend of NetworkX. So they can, it's opt-in. You can download NetworkX and the Python bindings and the SweetSparse library and convert your NetworkX graphs into SweetSparse graphs and call the same algorithms for a subset of them. And you can get anywhere from a speed up of 3 or 4 on moderate sized graphs to speed ups of 5, 6, 7 orders of magnitude on really large graphs. There are some graphs that NetworkX can't complete on that this process can complete. So technically, it's infinite speed up. So really exciting stuff, and we hope to get some uptake on that perspective there. And like I said, I've transitioned to the C++ API specification. There's work going on the spec in GitHub, so you can see where we're at on the spec. And there is a reference implementation by somebody at Intel that's going along with the spec writing. Let's see. I think after C++, we're going to focus on distributed. So with that, I will say that there is a website to get more information, graphblas.org. There is a mailing list that you can ask questions about, and you can send an email to Aidan Baluch at Lawrence Berkeley to get on that list. And there is a monthly teleconference. So if you're interested in hearing what people are talking about, you can zoom in there. With that, I will take any questions. Probably for the people online.
Thank you. Just a quick question. In the binding list, you mentioned Postgres, I believe. Can you maybe give additional information about Postgres and the GraphBLAS bindings to it?
Scott, let's see if we can get two microphones working via miracle of modern technology.
So the Postgres thing was an effort, 2-3 years ago by Michael Pelletier. It is nascent right now, but if there is interest, I'm sure we could update it. I don't know that much about it. I don't know how much of the API was implemented, but it is possible, and it is open source if you want to find out more about it.
Hello.
Hello. Yes. So actually, I have a question related to this work. Whether also supports data associated to the nodes and the edges, or just preventing as a matrix representation them, like to see the matrix representation adjacency list.
Could you say the very first part of this?
Oh, no worries. So whether the system is also supporting the data associated to the nodes and the edges.
Yeah, what do you mean by support?
Yeah, actually, I'm writing on that because there should be a system developed by Microsoft and Rice University, which is actually providing tensor representation of the data, and actually also provides like numerical representation and by hashing also string representation of the data, and it could also perform like graph algorithms or Markov chains. So I was also interested whether also this system supports data like property graphs, or is just meant to be used for a matrix representation of the data. That's it.
I have a couple of questions, and I know Tim wants to chime in.
Well, it's just, that's my talk. So,
Yeah, so there's
Stay
a
tuned.
talk at the end of the day on putting tile DD behind this. The short answer is the API specification says the data structures are. I'm getting echo. Where do I stand?
grab that microphone again.
Or just
I switched it off.
Yep. Okay. The API specification doesn't say a lot about the data types that can be stored. In the C API, there is a restriction that it has to be mem-copyable data types, which basically means it needs to be contiguous blocks of memory. It has to be fixed size. In the C++ API specification, we are working hard to improve interoperability with other data types, and so that we can make connections to other data types a lot easier, and we can support, with cost, dynamically sized things. So there's a lot of research to be done. The specification was put in place to kind of not prevent activities in this space. And then Tim will have more to say about that.
Thank you.
Anybody else? Good morning.
This is my recurring question. Do you see any uptake with the new AI accelerators like the Cerebras, the SambaNova, GraphCore, and so on?
I don't see uptake in what you mentioned, but Kata is writing or has written a GraphBLAS implementation for their thread migration architecture, and so that's exciting. I think
NVIDIA for GPU.
Yeah, NVIDIA's been working hard with Tim Davis on SweetSpars for a GPU backend, and they're putting the entire JIT process in place, which I like because now I can JIT from C++ directly templated stuff and get the same benefits as well.